Okay, so just gave some exams back, and you're welcome to come by and see me to talk about your exam if you'd like. Now, and then today's homework assignment was postponed until tomorrow because we're going to learn how to do that today. And so we're going to do two things today. First, we want to take a look at, finish up how the compiler translates if statements and loops, actually loops. We started that last time. And then a big topic that's going to be, we're going to expand on from now on till through the rest of the course. We're going to learn how the compiler translates assembly language statements to call a function. All right? So this will be this is a core, this is some key topics, some key ideas here. So first let's go back and do a little review of what we did last time. Here in figure 6.10, we have a while loop. And we took a brief look at how this while loop gets translated, but let's just review that for a second. So here we have the statement, while letter is not equal to asterisk. Now, where is the test for a while loop? At the top of the loop or the bottom of the loop? It's at the top. So now, do you remember how this would get translated? This while letter is not equal to asterisk. How would that be translated? Load byte accumulator what? Letter, and is letter a local or global? So that would be load byte accumulator letter addressing mode. Okay, load byte accumulator letter direct. And then compare that with what? What was the next one? Compare byte accumulator, so that's CP, right? Compare byte accumulator, the asterisk addressing. And then now what was the next one? When do we want to branch around to the bottom? Yes, when it's equal. So this would be BR EQ to end while. Okay, so everybody, so let's see if that's the way it was. Load byte accumulator letter direct, compare byte accumulator, and then asterisk immediate, and branch if equal to end while. So everybody see how that works? And then at the bottom, notice that at the bottom at location 002B, there's a branch back up to the while, so that you can, and that has to be explicit in the assembly language code. Are we good? Any questions about how that works? And then there's an if statement inside of that. Does everybody see how that works? Okay, and so here in figure 6.11 is the HOL6 on part A. So you have the while, and you have the braces, and you have indentation, and you have none of that at the assembly level. Okay, so you actually have to do explicitly branch back up and branch around, so all these branches. Okay, now how about in figure 6.12? Here we have a do loop, so we say cop and driver are global, so cop gets 0, driver gets 40, and then do. So now where is the test for this loop? At the top or the bottom? At the bottom. So now we just do, how would we do cop gets 25? Sorry, cop plus gets 25. How would you translate that? Yeah, that's right. Load word accumulator what? Cop. Add accumulator 25 addressing mode. Immediate. And then what? Store word accumulator to cop direct, because it's a global allocated with dot. All right. And now how about let's see if we can do the test at the end. Let's see if we can do the test at the end. While cop is less than driver, what would that be? Load word accumulator, cop. Is it a global? Direct. And then what? Compare word accumulator what? Driver. Is that also direct? Because it's a global. And now, when do we, so if that's true, we do what? We go back up to the, so we want to branch, now does everybody see what's next? Branch if what? Well, is it greater than, or is it branch of GE or LT? Well, that's the question. What do you want? Okay, so when do you want to go? Because it's while cop is less than driver. So if that test is true, you want to do what? Go to the top. So now what is it? Branch if less than. Now, is everybody clear on that? So this is going to be BRLT to while. Or sorry, to the do. Sorry, to the do. Does everybody see how that works? You got to just think it through what the logic is, what you want the, where you want the control, how you want the control to happen. So let's see if we did that right. Load word accumulator here starting at 0025 in figure 6.12, the second part. Load word accumulator cop direct, compare word accumulator driver direct, branch if less than to do. And then do is up at the label up at the top. Is everybody good? Are we good? Okay. And here in figure 6.13 is the structure at level HOL6 and at assembly level 5. And now it's a little bit more complicated with a for loop. Because what does a for loop have? It has these little 3 compartments in the paren, right? It's for paren, and then what, so what happens? It's like for I gets something, I less than something, I plus plus, whatever. So there's 3 little things to it. So what do you have to do? What does the assembly code have to do? You got to initialize the control variable, so whatever the initialization is. And then you got to test the control variable, and you got to branch accordingly. And then you execute the loop body. But then what happens after the loop body? You got to do what the third part of the for statement down at the bottom there. You see what I mean? And then branch back up depending accordingly. Does everybody see what you have to do? So the assembler has to put in all that code at those various parts. It's got to put in code at the top of the loop and code at the bottom of the loop. And then it's got to branch back up to the top accordingly. And it doesn't branch back up to the initialization part, it branches back up to the what? To the test part. Is everybody, are you with me on this? Yeah, question? Well, not necessarily, because whenever you write a while loop, your code explicitly initializes and tests. You know, I mean, you just write them in different places, so not necessarily. So in terms of execution, fors are just as fast as whiles. It's just that what's more convenient for you as a programmer to write? Which way is more convenient for you to write? So here in figure 6.14 is a really short program. We have int j, now this time it's a local, and we say for j gets 0, j less than 3, j plus plus, and then just a little output statement, printf j equals, and then the value of j, and then a new line. So now how would you do j gets 0? Load, not byte, load word accumulator, 0, no, you have to initialize. How do you do j gets 0? Come on. Load word accumulator what? 0 addressing, immediate. Store word accumulator to j. Now, j is local or global? So therefore what addressing? S. And then how do you do j less than 3? Here, let's do the j less than 3. Because that's the test. That's the test, right? So what would that be? Let's not optimize. Let's just, so if you just said j less than 3, what would that be? Load word accumulator, j, addressing, s. Compare word accumulator, cp, compare word accumulator, what? 3, addressing mode, immediate. And now this test is at the top. Now, Now, when do we quit the loop? Yeah, so it's BRGE is correct. BRGE to end for. So everybody see how that works? And then blah, 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 all that output stuff. And now what has to be at the bottom? J++. So how do you do J++? Load word accumulator what? Addressing? Okay, you guys are good. This is good. And then what? Yeah, add accumulator what? Add accumulator 1 immediate. Good. And then what? Store word accumulator JS. And then what do you have to do? You got to branch back up to the test of the for. Okay, so, and that's unconditional. Are you with me? So BR to for, wherever that is, up here. So here's the complete thing. So did we do this right? You see, oh, look here in figure 6.14 in the code. We actually optimized, right? You see the for on line 000C. We knew that J was going to be in the accumulator. Does everybody see that in 000C? We knew that J was going to be in the accumulator, so we didn't do the initial load word accumulator J at 000C. Okay, here's the point. In figure 6.14, we did not do this. Before the compare, we did not do the load. So in figure 6.14, this is what an optimizing compiler would do, because it would know that the value of J was in the accumulator. Now, how would it know that? Because if you're coming at it from the top, it's load word accumulator 0 immediate, store word accumulator JS. So the accumulator has the value of J in it because of that. And if you're coming at it from the bottom, you're adding 1 to J, so there's a J in the accumulator for that. So therefore the code omitted this before it did the test. But that was because it was an optimized. This is an optimized. This is what an optimizing compiler would do. Is everybody clear on this? We talked about okay. What is an optimizing compiler? Fast to compile or fast to execute? Which? Fast to execute. And so a non-optimizing compiler is what? Fast to compile. Are you with me? Does everybody remember that? Okay. Any questions about this one? Okay, now here's an interesting question. You know, we have all these. What we've done is we've taken a look at if statements and for statements and while statements and do statements, and they have, and what we have, the way we have to do it is we have to have these branches, right? Now let's take a look here at figure 6.15. Can you tell me is this an if statement or a loop? Well, yeah, but what kind of a loop? I mean, can you tell what kind of a loop that is? I'm not sure you can do this kind of a thing in a high order language. I mean, you know, look, do you agree that, we're not talking about a compiler now. Suppose that you are an assembly language programmer and you have this unconditional branch and you have branch if EQ, branch if less than, blah, blah, blah. Do you agree that you could just branch, the sky's the limit? You could branch it, you could branch here, you could branch there, you could branch down here. You could be in a loop. You could have a loop up here, and you could somewhere down here you could have something, and you could branch to the middle of that loop, and boom, boom, boom. Do you agree that you could do? I mean, it's legal to do that in assembly language. So do you see that apparently there are some things that you can do in assembly language that you can't do in an HOL6 language, like in C, that corresponds to, you know. So now here's are you with me on this? Okay. In fact, here I challenge you in figure 6.16. Look at this. Here is a program, and look at here, it has main and deci, blah, 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 and this L1, deci, blah, blah, blah. But look what it says. branch if less than, look on line 0021, branch if less than to L7. L7 is way the heck down here, right? And then up here, and then it says branch to L6. So you branch to L6, you come down here to L6, and what happens is branch if less than or equal to L4. So it goes up to L4, 0049, blah, blah, blah. Are you with? You see how this branches all over the place? So look, here in figure 6.17, when you have an assembly language program where these branches just go all over the place, there's a name for that. It's called spaghetti code. And why is it called spaghetti code?
It looks like
Because those arrows all look like a bowl of spaghetti.
That doesn't sound like a good thing.
Right. In fact, here's the thing. You can write spaghetti code in assembly language. But if you're writing in C, you have to have what? Ifs, loops, and furthermore, an if has to be totally nested inside of a loop, or a loop has to be totally nested inside of an if. You can't have the boundaries like this. You can have an if inside of a loop or a loop inside of an if, but you can't have it like this. Do you see what we're saying? So that means that there's limits as to how you can structure your flow of control. And so if you're limited to just if statements and loops and just sequential, that's called structured flow. Otherwise, it's called spaghetti code. Yeah.
So is that the whole reason for HL6 existing?
That is one of the benefits. That is a primary benefit of HL6 languages, is that it limits you to structured flow of control. But I'm telling you guys, in the early days, there were no HL6 languages. And people did used to write spaghetti code. And they thought it was cool. I'm serious. They thought it was really, they're very clever things. We'll branch to here, we'll branch to here, it was, you see, now this raises an important theoretical question. This raises an important theoretical question. Here's the question. Do you think it's possible to write an algorithm using unstructured flow of control that's impossible to write using structured flow of control? Because like we're saying, with unstructured, you can branch into the middle of a loop. So you suppose there's some computation that you can do with just gotos that you can't do with ifs and whiles and fors? You understand what the question is? It's a theoretical question. In other words, are we limited to what we can compute if we are only limited to if statements and while loops? Can we do everything that's possible to do with computation with just if statements and while loops and sequence? Or is there some stuff that we have to use unstructured flow of control in order to actually compute it? You understand what the question is? In other words, is unstructured flow of control more powerful? Can we do something with that we can't do with just if statements and while loops? Yeah, it's not. And that is the result of an important theorem. It's called the structured programming theorem. And the structured programming theorem was proven in 1966. This is when HOL languages were starting to really get a foothold in the industry. And the structured programming theorem says any algorithm containing gotos, no matter how complicated or unstructured, can be written with only nested if statements and while loops. And a couple of Italian mathematicians, Bowman Jacopini. Yeah, actually, that's a good point, and that's what they did. What they did is Bowman Jacopini, in order to show that it was equivalent, it's a construction proof. They were able to say, okay, if you have a chunk of code that doesn't have, that's a block that doesn't have a branch into it, and they divided it all up into that, and then they showed that, kind of like graph theory. No matter how you did it, you could make this the body of an if, you can make this the body of a while, and you can actually transform it into structured. So they proved that it was possible. But now look, you guys, they proved that it was possible. But now here's another important thing about our history, the history of computer science. They proved it was possible, but then there was a guy, his name was Dijkstra. Have you ever heard of, have we mentioned Dijkstra? We've mentioned Dijkstra in several of our courses because he did a lot in a lot of different areas. And what Dijkstra did is Dijkstra, as shown in this slide, Bowman Jacopini showed that it was possible to write any algorithm without gotos. But Dijkstra said, not only is it possible, it's better. Do you see what he's saying? He was saying it's not just possible, it's better. And he waged a war against goto statements because in the day, in the 1960s, HOL6 languages still had goto statements. You know, you could say go to L1, and you could put L1 colon, and you could go to that in the middle of a loop. You could do that in HOL6 languages. And look at what he says. This is a quote. More recently, I discovered why the use of the goto statement has such disastrous effects, and I became convinced that the goto statement should be abolished from all, quote, higher level programming languages. This was heresy at the time. The goto statement as it stands is just too primitive. It is too much of an invitation to make a mess of one's program. He wrote this in 1968, 2 years after Bowman Jacopini's paper. And it set off a firestorm of protest. There were letters to the editor, no, because, and you know what the big argument was? The big argument was, with gotos, it's more efficient. So they said structured, it's less efficient. And then people debated about why it was efficient and why it was less efficient, and then people, you know, it was huge. It was called the goto controversy. But what happened was, it turned out Dijkstra was right. And over the years, people have gradually accepted the fact that it's better, structured flow of control is better, you know, and it's just as efficient as unstructured flow of control. And the reason is because of maintenance costs. Can you imagine what it would be like to maintain a program that had just goto statements all over the place? It would be horrible, and time is money. So to maintain programs with unstructured flow of control is so costly that nowadays everyone realizes it's not even an issue anymore. Everyone realizes that structured flow of control is good, and all modern programming languages now don't even have the goto statement anymore. Even though HOL6 languages used to have goto statements in them. Now they don't. You know, they were like, by goto we mean branch, you know, conditional and unconditional branches. Yeah. So anyway, that's an important part of the history of computing, is the famous goto controversy that was initiated by Edgar Dijkstra. Okay, so that's the first part of our goal for today, was these flow of control issues. And now the second thing that we want to do today is to learn how the compiler translates function calls. Now, what we're going to need now are two new instructions to call a function. All right? The first instruction, assembly language instruction, is the call instruction. The mnemonic is CALL. The instruction specifier is 0010010A. And so it's like a branch instruction where there's two addressing modes, either immediate or indexed. All right? And now this one is an important one for us to understand the register transfer language. Look at the register transfer language for the call. What's the first thing that happens automatically when you execute a call statement? SP gets what? SP minus 2. Now what does that do? Are you with me? The stack pointer goes up by 2. Then what happens according to that RTL? So now we're going to put something there. And what are we going to put there? The contents of the program counter. Now what does the program counter have in it? The address of what? Of the instruction to be executed next. And that will be the instruction. What instruction will that be? That will literally be the instruction where. Right where. No, this is a super important concept. Look, what's happening is we have some instructions here. Blah, 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 blah. Here we have a call. Call my function. That's too long. Call my fun. Call my fun. And then we have, I don't know, blah, 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 blah. Now, we are executing this function. Now, sorry, we are executing this statement. Now, what's the von Neumann cycle? Fetch. So we're going to fetch the call. Then what? Decode the call. And then what? Increment the program counter. So what will that make the program counter? That would be the address of this. And then what? Execute. Now, when we execute, what happens? This says what happens when you execute. What happens? The first thing that happens? SP is SP minus 2. Now tell me, what does mem sub SP get? So what address is that goes into the mem sub SP? Say it again. Well, what did we say the program counter is at this point? The address of what? Of the what? Of the statement after the call. Is everybody clear on this? This is super important. Are we getting it? And then what happens? PC gets what? The operand. So now PC is going to get my fun. So the next instruction to be executed will be what? Wherever we're branching to for the function. But what will be on the runtime stack? The what? There will be the address of the instruction after the call. This is how the return address gets pushed onto the runtime stack. Do you remember how we've memorized this? And how we've drawn pictures of ret address? This is it. This RTL is it. Here, let's say it again. Here, let's just suppose that this is load word accumulator data direct. All right? So look. Now, so here, what's the von Neumann cycle? Fetch, decode, increment, execute, read. So we fetch, so here, the program counter is here. We fetch the call instruction. Then what do? Decode it. Then what do? Increment the program counter. So now the program counter is what? Is the address of this. And then what do? Execute. But what does the execute do according to this RTL? It does SP gets SP minus 2. And then what? Memory sub SP gets what? Program. But what's the program counter? It's the address of this. So that's going to mem sub SP. So that's the top of the runtime stack. And then what happens? Program counter. So the program counter gets the address of my fun. And so the next statement to be executed will be my fun. But what will be on the runtime stack? The return address. So that whenever we, are you with me? So we will know. So the system will know. The system will know how to get back to here. Now, how does it get back to here? That's another instruction. That's called ret. Is everybody clear on that? Is everybody following the concept here? So, and what does ret stand for? Return. And this is a unary. The instruction specifier is 0000, 0001. There's no addressing mode. There's no nothing. It's just unary, no operand specifier. The mnemonic is ret, and what does it do? It assumes that the program counter, it assumes that the stack pointer is pointing to the what? on the stack, it assumes that the stack pointer is pointing to the, is the, no, it's the address of the, that got pushed onto the stack. Yes, that's right. It assumes that the program counter is pointing, sorry, it assumes that the stack pointer is pointing to the return address that was stored with the call. And what does it do with it? PC gets what? Mim sub SP. So that puts that return address into the what? Program counter. Yeah, and then it does SP gets SP plus 2 because that pops it off. And now the next statement to be executed will be what? The statement where? After the call. Ah. Does everybody get this? This is all very mechanical. That fetch, decode, increment, execute, repeat is wired into the CPU. These statements for the call, SP gets SP minus 2, mim sub SP gets PC, PC gets operand, that's wired into the CPU for the call. And this RTL for the return, PC gets mim sub SP and SP gets SP plus 2, is wired in for the execution of the call. Is wired in for the execution of the return. And so that's how you get the return address, that's how you get it on, that's how you call and how you can return, with call and ret. Okay, so here, let's do an example. Here's figure 6.18. Now, figure 6.18 is a function with no local variables, no global variables, and no parameters. So what's on the runtime stack for this? Just the what? What does the runtime stack look for with this? Just the what? No globals, no locals, and it's void. So how big? What does the runtime stack look like? No, well, come on. What happens when you what happens when you call a function? Storage for the return value. This is void, so there's none of that. Then what else? The parameters. No, hold on. The parameters are second. What's third? Return address. Okay, so we do have a return. And what's next? Storage for the local variables. But there's none of those. So how big is, so what's on the runtime stack? Just the return address.
Well, when we've been doing it with the ones that...
Yeah, we've always had the return address when we call a function. That's the one thing that's always on there when you call a function. Because the 5 things are storage for the return value. What's next? Storage for the return value. What's next always? Actual parameters. What's next? Return address. What's next? Storage for the local. I said 5. I meant 4.
Well, just like the other...
With the runtime stack for the main program, we sometimes omit that for simplicity,
Okay.
but it's always there.
Is it before those?
It's when the operating system calls main.
Well, right, but if you're drawing the stack?
No, it doesn't, because the stack pointer is on the top, and it's the
Oh, okay.
and it's down from the top.
Okay.
Yeah. Okay, as everybody, that's a good point. That's one thing that makes this not quite so clean is the fact that the main is a function call from the operating system. But we included that early on in our presentation, but then after a while we ignored it.
Okay.
Yeah, that's what was throwing. Yeah. Good point. I'm glad you brought that up. All right, so now look. Let's see if we can translate this. First of all, what's the first statement going to be? What's the first statement going to be? Branch to what? Main. Okay. But now what's going to happen is we're going to have this code for print try. Now what's going to be the code for print try? So here's a little print try, little documentation for print try. And now what is print try going to be? It's going to be what? A print, that printf. How will we execute that printf? How will we translate that? A stro, and then what about the next printf? Stro, another one, what? Stro. So this will be like stro. stro blah blah blah, stro blah blah blah, stro blah blah blah, stro blah blah blah. Right? And then, yeah, question?
For the new line though, will you have to have like the load then?
Well, no, we can include those in the string. You know, we can do the bash. Yeah, we can include those in the .ASCII strings. Okay? Then we have the .ASCIIs, blah, blah, blah. All right? And then what's going to happen is the last thing here will be a what? Will be a ret, a return. And then when we branch to main, main will be here. Oh, and furthermore, what will we call? We need, yeah, this, yeah, we need a symbol of print try for the first statement in here. See? So this will be print try. Do you see how that's going to work? And then what will this main be? This main will just be what? No, not branch. Now this will be call. See? So this will be what? Call print try. Print try. Call print try. Call print try. How many times do we call it? 3 times? Call print try. And then stop.end. Except we'll have the .ASCIIs for our messages. Yeah, see, if you did a branch here, if you did a branch to here, it would branch boom, 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 boom. And here when it does a ret, there wouldn't be a return, it would be unpredictable because there wouldn't be a return address in the...
Okay.
See, so this assumes that you did a call.
And if you didn't have, like, just pretend you didn't have the ret there and you just did branch.
And if you didn't have a ret here, it would come here and it would call, it would call, and it would call, yeah, or it would branch, yeah. It would be an endless loop, yeah. Does everybody see? Yeah, question?
Not necessarily.
Yeah, it's perfectly legal in an HOL6 language to have a function call another function. In fact, it's common, and we're going to do it. Yeah. Then there will be another, yeah, there will be a function here, the main here, a function, and could call the function. Yeah, that's quite common, and we'll do it. Yeah.
So to store
Return statement.
return address.
Well, the call is what stores the return address. The return is what pops it off the stack and uses it to get back to the statement after the call.
So yeah, okay.
Notice you can't have a branch here because where would you branch? Would you branch to here? Or would you branch to here? Or would you branch to here?
Yes.
See, you don't know. So that's why you need the return address. That's why you need the return address. That's how function. This is how, in assembly language, what the compiler does to translate a function call. It's because you can call that function from several different places.
And then it wouldn't know where to go.
And it would know where to go back to in the code for the function. So that's why the return address has to be put on the runtime stack. Yeah, you could store that return address somewhere else in memory, but think about this. What about a recursive call?
So you have to know where
See, so, you have multiple return addresses.
it'll just,
So then, yeah, so that's why it's on the runtime stack.
yeah.
So here is, in figure 6.18, the continuation of it. Here is the actual code. Yeah, question? Yeah, but does that mean, yeah, but that means is my figure in my book incorrect? Is this a bug in my book? Yeah. Okay, you get bonus points for typo in the book if that's what it is. Okay, so now here's a little, in figure 6.19, here's a picture. Now look, let's take a look at figure 6.18. When we make the first call, that call is at 0019, right? And so what's going to get pushed onto the runtime stack for the return address when we execute that call? Should be 001C. And see here in figure 6.19b, that's 001C. Yeah.
How does call be?
Call is not a unary instruction. Call is a non-unary instruction.
Oh.
And so that will always be 3. When the program counter gets incremented because of the call, it'll be incremented by 3. And therefore, it will point to the statement after the call. Okay? Are we good? All right, so now comes, oh shoot, we only have less than 5 minutes. Let's get this started and we'll finish it up tomorrow. You can study it, and I think we can still have the homework due tomorrow. But here's the concept. To call a void function in C, now there's no return storage for the return value. So you push the actual parameters, you push the return address, and you push storage for the local variables. Now here comes, you guys, you've memorized this before, but now we're going to see how it actually works in practice with the compiler. And here is the deal. In assembly language, you understand, this is the caller, the function is the callee. All right? So this is the caller, this is the callee. Now watch. The caller pushes the actual parameters. Now we've seen how to push it. We've seen how to push something onto the runtime stack. You remember? We do it with sub SP. So the caller does that. Then the caller pushes the return address onto the runtime stack. And what statement does that? Call. All right? Now after that statement executes, where will we be? We will be in the, after that statement executes, where will we be? We will be where? In the callee. So what does the callee do? Yeah, that's the callee's responsibility for allocating. The code for that is up in the callee. Are you with me, sports fans? Okay? So the callee allocates the local. Now those three things are on the runtime stack. So now what happens? The callee executes its body. Right? Now after the callee executes its body, what does the callee have to do before we can do the ret? Yeah, it has to pop the what? The local variables. So the callee pops the local variables. And how does it pop the local variables? By doing what? Add SP, yeah. Okay, add SP, right? And now where's the stack pointer? Now what's the stack pointer pointing to? It's pointing to the what? To the return address. So who pops the return address to get back to the statement after the call? The callee pops the return address by executing ret. And now where are we? We are at the what? Statement after the call. And so now what does the caller have to do? Yes, it has to pop the actual parameters by doing the add SP. So now do you see where this code is? So you see where this code is? This code, you know, to make one function call, there's some code before the call in the caller, then we get up to here, and then there's some code in the callee. And then it executes, and then there's some code in the callee, and then does return, and then there's some code in the caller to do the return. Does everybody see? And this is how those runtime stacks those stack frames get constructed during execution. It's by having this code in these different places. Some before the call, some before the execution of the body of the function, some after the execution of the body of the function, and some after the execution of the call. Now, does everybody, you see how that works? And so what we're going to do tomorrow, you can study this to do your homework, but what we're going to do tomorrow is we're going to walk through this figure 6.21, which is a function call with global variables and a print bar function with a local variable with a parameter called n. And I encourage you to study that, and we'll go through the details of this tomorrow. All right? Good deal. See you tomorrow.